Having said that, I want to introduce our speaker. Today's presentation is on organic batteries for energy storage. Our speaker earned his bachelor's degree at Benedictine College in Atchison, Kansas, the home of the Ravens, not to be confused with Benedictine College in Lisle, Illinois, the home of the Eagles. He earned his master's degree and his doctorate at the University of Rochester. And it was there that he investigated electron transfer reactions that play such a critical role in the conversion of solar energy. He later went to the California Institute of Technology to perform postdoc studies. And during this time, he learned the basics of electrochemistry, which, as you will learn, served him later in his career. And he also studied the polymerization of metal complexes. He joined the faculty of the University of Kentucky in 1986. And while he was there, he investigated the electrochemistry of fullerene. An interesting connection here. The chemist Richard Smalley was on the team that discovered fullerene. Richard Smalley was a student at Hope College in his freshman and sophomore years. He then transferred to the University of Michigan. He worked on fullerene, and for his efforts, he shared the Nobel Prize in Chemistry in 1996. In 1994, Dr. Guarr, our speaker, joined a small company in West Michigan called Gentex Corporation. It was smaller at the time. He was hired as assistant director of chemical research, worked his way up the ranks, and became vice president for chemical research and aerospace technology. Gentex developed electrochromic devices for the automotive and aerospace industries. Dr. Guarr will give us a glimpse of what some of that work resulted in. The outcome of the research at Gentex spawned a number of patents as well. Dr. Guarr went on to Michigan State University's Bioeconomy Institute, located here in Holland. 10 years ago, he co-founded Jolt Energy Storage Technologies and serves as its chief technical officer. We're all aware that energy from renewable resources such as wind and solar isn't always available. The challenge is to store that energy so that it is available when it's needed. Today, we'll learn how Dr. Guarr's interest in organic redox chemistry and materials science is taking on that challenge. So without further ado, join me in welcoming Dr. Tom Guarr.
Thanks, Louis. You just gave a great introduction for why we need energy storage to introduce more renewables on the grid. So I don't have much more to talk about, but I will do my best. We're here to talk about energy. And as you probably realize, humans have an incredible appetite for electrical energy. You can see that from this picture. We are using electrical energy at a very rapid rate, and it's increasing. It's expected to grow by 50% over the next 25 years or so. So how do we address that need? And there are multiple ways to address that need, of course. We could burn more stuff and generate electricity. I don't think that's a good option. I'm guessing that most of you here don't think that's the best option, if there are other options. So we're going to talk about organic batteries. And by organic batteries, I don't mean that we grow them without pesticides. I mean that the materials that are in them are carbon, hydrogen, nitrogen, maybe some sulfur and oxygen, but no metals. And in fact, even our electrodes are carbon. We don't use metal. Now, for the actual structure of the cell, we do use metal, aluminum, typically. But all the working guts of it are non-metallic in nature. So I'm going to go through and first of all convince you of the need for long duration energy storage, why it's important, and then I'm going to sort of walk you through the process of how we took lessons learned from a completely different industry and have applied them now to try and make a workable organic battery. There will be some chemistry in there. I don't know if your backgrounds include chemistry. There will be some. I will give a little bit of a primer on defining some terms, and I'll try and keep it 30,000-foot view. So as far as the need for renewable energy, we've alluded to now several times. And everybody has probably seen a graph that looks something like this, where carbon emissions have grown pretty dramatically, particularly since about 1950 or so. What you probably haven't seen is a graph that looks like this. And this is a dynamic graph that I'll start in a minute, but I want to explain some things first. It's basically a chart of average global temperatures by month from 1880 to, I think it goes to 2020 or 2022. And the green circle, if you can see the green circle here, oh, it's a bad angle. That represents the average temperature, global temperature in the 1850 to 1860 time frame. So back from my childhood. So if it stayed exactly that temperature every year, it'd be a really boring graph just going around that green circle. But here's what it actually does. In the late 1800s, a little bit of cooling. So we saw sort of below average temperatures. Starts to warm up just a tiny bit. And you'll notice in the 30s, it's a little bit of cooling. That happens to be Dust Bowl era. So we weren't getting as much sunshine. 40s warmed up a little bit. There was something global conflict in the 40s. As we get to later years, we're starting to see a little bit of an increase in temperature. Average global temperatures again. And we're now approaching the 1 degree C or nearly 2 degrees Fahrenheit. And if we take a little bit closer look from a different angle here, we see that recent years have been dramatically warmer than past years. And in fact, of the 10 warmest years on record, all of them have occurred since 2010. I don't have 2023 data, but I think it's the new top. So correlation doesn't prove causation, but this is a pretty good correlation. And at least the models show that it's likely that the first graph caused the second graph. So let's take a little bit of a look at why we need, or first of all, where our electricity comes from. And this is a little bit of good news, bad news. So if you see here, early on, up to even about 2000, the year 2000, coal was an extremely important source of electrical energy generation. The good news is that the use of coal has fallen off pretty dramatically. And I've said this in a talk before, there's no such thing as clean coal. So that's good news. The increase in natural gas use is primarily due to the decrease in cost of natural gas. So that's become a very important component. And then you'll see kind of at the very top, increasing contribution from wind and solar. Again, good news. So the total annual electricity production in the US is about a little over 4,000 terawatt hours per year. Nobody knows what a terawatt hour is, but it's a million kilowatt hours. So it's a million or billion. Anyway, it's a lot. So it's, and we use about a fifth of the global total. And if you're counting calories, that's a bunch of calories. I don't know what that number is. So one thing that you'll notice about this graph is a pretty significant increase in annual electricity generation in the US. Pretty dramatic. It's gone up more than a factor of 8 in over the time period of this graph, up to about year 2010 or so, and then it levels off. Does anybody know why it levels off? I didn't know. I thought it might have been rooftop solar that people were help powering their own homes, and that's not captured in this electrical energy generation. That's not it. Most of it is due to LED light bulbs. Much more efficient than the old incandescent. And it turns out to have a pretty dramatic effect on how much electricity that we use. So that's a good thing also. So more good news. The cost of generating electricity from wind and solar are at historic lows. And in fact, the cost of generating electricity from wind and solar now in most of the US is lower than generating electricity from natural gas. That's pretty cool. As a result, we're starting to see new records set. I thought I'd just put up a couple plots here of where, first of all, solar energy in the top graph, where our solar energy comes from. See, Texas and California are big contributors. And then also we have the fact that there was a new record for generating electricity from wind and solar was set in 2022. I couldn't find anything more recent. But the amount of electricity from wind and solar, if it hasn't passed already, is poised to pass that from coal pretty soon. Again, good news, I think. So we have the first of our duck curves. I'm going to show you other duck curves, which means something entirely different later. But if you look at that top blue line, that's the demand. Fairly flat through the morning, dips a little bit in the afternoon, and then increases fairly dramatically. Oh, sorry about that. I apologize. Back. So that's our total need for electricity. Now, typically, solar contributes a lot to the electricity generation. And obviously, we generate a lot more of that during the day than we do at night. And so there's an excess of electricity during the afternoon because of the contribution from solar. However, we still have to build our electrical plants to cover the demand in the morning and even more so in the evening. And we're throwing away a lot of that solar energy that we generate during the day. So what's the answer? Well, the answer is energy storage. Sun doesn't always shine and the wind doesn't always blow. We need to save the electricity that we generate when it does to use at other times of the day or month or year. And recently the DOE committed a significant amount of money, $158 million into investigating ways to store energy, especially long term. Now, what are our options? Well, there's lots of options. There's pumped hydro, and that in the upper left-hand corner That's actually a facility in Ludington here. And the concept here is to, when you have excess electricity available, you pump the water uphill, and then when you need the electricity, you let it fall down, turns a turbine, generates the electricity back. This is actually a pretty good way to do it. Pumped hydro is fairly important and a good contributor to our energy storage technologies. However, it works really well when your power plant is in between a lake and a hill. That's not always the case. I grew up in Kansas. We don't have either of those things. And it's really expensive to build, as you might imagine, especially if you have to build the hill. And there are other problems. There's potential fish kills, there's maintenance on pumps and all of that. But overall, it's a very good technology where it's applicable. It's hard to get permits. So there's only been 2 or 3 built in the US in the last 30 years. Most of them are old. The next competitor is compressed air. I hate this one. The idea is to take an old abandoned mine, seal it. When you have excess energy, you pump air into that at high pressure. And then when you need it, you let the air out. Again, turns a turbine, generate electricity. To me, this is nuts. I don't know how you seal an old abandoned mine that well. And in fact, the efficiency of the pumped hydro is like 92% or something. The efficiency of the compressed air is like 45%. And again, you're still limited in where it's applicable. Your power plant has to be near an abandoned mine. So this is not gaining much traction. One thing that is the lower left-hand corner there. And this is the best picture I could find of it. This is a gravity-based energy storage system where huge columns of concrete are lifted up when you have excess energy. And then when you need energy later and don't have enough generating capacity, it's allowed to, gravity is allowed to take over, bring it down, and that motion then generates electricity. It's kind of an intriguing system, and I think it could find some applications. Kind of expensive to build. And I think to me, it's a little scary, but that's just me. And probably the most flexible option is batteries. And you can see that in the lower right-hand corner, generic battery, because when you say you're going to use batteries, the next question, oh, I'm sorry, I introduced this here. This is just to show where our energy storage capability comes from. Early on, and by early on, I only mean 15 years ago, it was pretty much all pumped hydro. And it wasn't until rather recently that we started getting some battery storage. And this is a little bit of a confusing graph because the different colors are just different length of storage. So now we're going from 2-hour storage, 4-hour storage, 6, 8, and 10. And we're increasing the length of time that we can store energy as we move forward on the calendar. By the way, I forgot to mention, if you have questions during the presentation, feel free to ask. I'm fine taking them now or later or both.
Second.
That pool in Ludington, is it cement? Is the pool cement like a pool in your backyard? How is it is it cement? What is it?
So the question is, in the Ludington facility, what is the construction of the pool of water? And I haven't actually seen it, but I believe it's concrete. Yeah, it's concrete wall. So that I do not know. Okay.
Hold on a second
Oh.
here.
The hours here, that's the storage begins to lose energy. And that's why it's limited in the time it can be stored.
So the question was the time frame of energy storage. What determines that time frame? Part of it is simply cost. So you can store enough energy for 2 hours for a limited number of batteries. If you want to store it longer, you have to have more batteries. So that's part of it. Part of it is losses over time as well. Part of it is just technology is not, some of the early technologies were not very well suited to longer term storage, but most of it is just cost.
I'm assuming that most of your talk will be focusing on large volume storage, but I'm also having in the back of my head questions about storage at home if I put solar panels. So as appropriate and when you can, if you would maybe differentiate a little bit or comment about the how your research applies to a home situation.
Sure. So the question was about whether this is going to be the topic that I'm going to get to here shortly is going to be about large installations for energy storage or smaller ones, even as small as a home. And I'll talk a little bit more about it later, but a lot of it comes to initial markets and cost reductions with scale. And then there's just some technology differences.
Does this graph represent also different types of batteries, different battery technologies, or just one type of battery?
So the question is, does the graph represent all types of batteries or just one? This is all types of batteries. And a lot of this, especially early on, was lead acid batteries, particularly after they've lived their useful life in your car. You can actually resurrect them to some extent, less efficient. But they're basically free at that point. That was used and still is being used. But there's other types of batteries out there as well. Okay, thanks for the questions. So when it comes to batteries, the next question is what type of battery? There's all sorts of batteries available. These are just some of them. They have different applications. There is no one technology fits all. And the example I always use that, if you need a battery for a pacemaker, lead acid is not a good choice. Right? But the one that people are probably most familiar with is lithium-ion battery. Again, there are choices. There are at least 6, and I think probably more than that now, commercially available types of lithium-ion battery chemistry. So do we use LMO, LCO, LFP, NMC, NCA, LTO? What do we use? They have different characteristics with how much energy they can store, how expensive they are, how good the lifetime is, how safe they are. All of these differ. So, sorry about that. I will try not to cough. It reminds me of a story, but tell it later. So lithium-ion batteries. So one of the most common lithium-ion batteries is called NMC. The M stands for manganese, L stands for lithium, M stands for manganese, C stands for cobalt. The problem with cobalt is that about 70% of the world's supply comes from the Republic of Congo, where it's mined by children. And this doesn't look like a picture of a mine, but this is a picture of a cobalt mine in the Republic of Congo. And you can see children, a lot of manual labor in an environment that's kind of toxic. Now, most of the mines, you have to be older than 12 to go down the deepest, most dangerous ones. But it's a problem. In addition to being a supply chain issue problem, it's a socioeconomic problem and a social problem. One of the other types of batteries that I'm going to talk to you about here very shortly is a vanadium battery. Some of you may have heard of vanadium. It is a relatively rare metal. It's not considered a rare earth, but it's fairly rare, which means it's expensive. That is vanadite, which is a vanadium ore that is mined and used in these vanadium batteries. And that's beautiful, right? That's really beautiful. The process of getting it is not so beautiful. We take beautiful land and we convert it into a giant pit. So not very efficient, not very sustainable. Lots of issues with the supply chain, which means it's expensive. So why not organic batteries? Now, many of you might think that organic batteries are nuts, right? Organic stuff is soft and squishy and not very durable. How can we ever use it for a battery, right? And I will point to, we talked about LED light bulbs before. LEDs used to be all inorganic materials, metal-based materials. Now there's OLEDs, organic LEDs, and they have some distinct advantages. You can now go down to your local electronics store and buy an OLED TV, 65-inch OLED TV for not all that much money. They have tremendous contrast ratios, beautiful colors. You know, millions of colors instead of the hundreds of colors that you get from inorganic LEDs. So they're fantastic and they last for a long time. So it is possible to make organic materials live in the real world in demanding applications. And I hope I can show you that a little bit further here. This is the vanadium system. This is called a redox flow battery. It's very different from your traditional battery. In your batteries that you're used to, everything is held in a nice convenient can or pouch. In a flow battery, you have tanks of the active materials, the highly energetic liquids that are pumped through a central electrochemical cell. Chemical reaction takes place, and the chemical energy in the fuels from the tanks is converted to electrical energy. I always use the analogy of a car. Unless you own an electric vehicle, then it doesn't work. But if you own a internal combustion engine car, you have a tank of a reactive liquid that's pumped to an engine. The chemical energy is converted to mechanical energy and you move down the road. This is a very similar thing. You pump the active liquid, in this case, 2 different liquids, to an electrochemical engine. The chemical energy is converted to electrical energy. One of the problems with the vanadium system, and there are some installations here. This is San Diego. They have a fairly large installation. I want to say 2 megawatt, 2 megawatt, 8 megawatt hours. One of the problems with the vanadium system is that the electrolyte is pure sulfuric acid. Actually, it's sometimes diluted with hydrochloric acid, but still not an insurmountable problem, but not a trivial thing to deal with. especially when that's right next to high power electronics. So obviously there's a lot of expense in safety precautions. So now we're going to take a little bit of a timeout and make some definitions. Yeah.
So for that battery, it sounded more like you fill it with two kinds of liquids and you get power out of it. How do you charge that? Like if you're doing the excess daylight, charging the battery for nighttime, how does that work with that battery described?
So very good question, which was how do you charge that battery? It looks like you take two reactive liquids and you generate electricity. Basically, to charge it, you run it backwards. And now you input electrical energy, run it backwards, fill the tanks with charged fuels. So it is really that simple. And I say simple, but it's not really. So first on this science lesson is energy versus power. A lot of people get this confused. Even some engineers get this confused. Energy is the capacity to do work, and power is the rate at which you do the work. So I'm going to show you two vehicles. First is I think we would all recognize that that's not very high power vehicle, whereas this one maybe has a little more power. They both have the same energy. They both have 1 gallon gas tanks. So the energy is in chemical energy, in the form of chemical energy for these vehicles. The difference is that the first one runs for 2 hours on that gallon of gas. And the second one runs for 8 seconds on a gallon of gas. So it is obviously much higher power output than the first one. So some of the other definitions, when I talk about potential, electrochemists use potential and voltage interchangeably. So it just means voltage. When I say reduction, that means we're taking a compound, a molecule, and we're adding an electron to it. And oxidation is the reverse. We're taking an electron out of it. Together, we use the term redox, which is not this facility in suburban Detroit. I took a field trip and checked, and it's not that. And we say something is redox active if it's capable of undergoing either oxidation or reduction or both. Okay. So now we have our second duct graph. And this is for an electrochemical technique called cyclic voltammetry. In this experiment, we apply a potential, and typically we'll increase that potential to a certain endpoint that we set. And then we'll reverse directions. So the potential is basically a cycle. We'll go, say, from 0 to 1 volt back to 0. And during that process, we monitor current. And you can see that the current increases, has a peak here at the top that's labeled oxidation peak. So we know we've taken an electron out of a molecule. And then for reasons that I won't explain, that peak falls off, forms a duct bill. When we reverse directions, we form the other half of the duct. So one thing that I want to emphasize is that we do this on all of the compounds that we make because it tells us, well, it gives us a hint at whether this is stable. For good behavior, we need a nice symmetric duct. It doesn't guarantee that this will live long enough in the real world. But if it's not a symmetric duct, if it's a half a duct, a duct with a tumor, a pregnant duct, flattened duct, we know it won't work. So we're going duck hunting. And this is one where now instead of ramping up the voltage, we ramp the voltage down and we generate a duck. Now there's some disagreement in our lab as to whether this is an upside down duck or a partially submerged duck. And I would submit that it really doesn't matter. It's a duck. And this is a pretty nice looking duck. Question over here.
So how predictable are these, whatever that's called, the cyclic
Voltammogram.
voltammogram, thank
Yeah.
you. Can you set the circumstances up and reliably get the same result time after time after time? Predictably?
So the question was, are these reproducible? I think is the essence of your question. Yes. Under the same conditions, they're very reproducible. Now there's thousands of things that can interfere with that. If you have a dirty electrode, for example, you won't get a good duck. If you change the temperature, you might not get a good duck. If you change the potential at a different rate, you'll get a different duck. And we are getting better at actually using molecular modeling to predict where the duck is and also how symmetric the duck will be. And you'll see some results of our molecular modeling here shortly.
Great, thank you.
So turns out that organic batteries already exist. Millions of them are out there. And many of you probably looked at one today, several times. At least I hope so. It's not your phone. It's in your car. And it's a weird battery. It is really a weird battery. And it's a weird battery because you can tell the charge state that it's in just by looking at it. I don't need a meter. I can tell you what the charge state is just by looking at it. It's also a really lousy battery because it stores a tiny, tiny, tiny amount of energy. And it also has a shelf life of about 10 seconds. Not a very good battery in that sense, but one very unique feature, you can charge and discharge this battery 100,000 times at high temperature. And by high temperature, I mean 150 F, and see absolutely no change in performance, and maybe 0.1%. So that makes it a very interesting battery from our perspective. And here's what it looks like. It's the rearview mirror in your car. It's now, I don't know exactly since I left Gentex, but probably in 40 to 50% of domestic manufactured vehicles and a very high percentage of some of the others as well. If you have an electrochromic, this is an electrochromic or sometimes called a self-dimming mirror. There's a 98% that possibility or probability that it is organic in nature. There are a few inorganic ones, but they don't work as well. And there's probably about a 92% chance that it was made down the street at Gentex. That's their market share. So I'm going to tell you a little bit about how that works, and I won't go very deep into it, but hopefully enough to give you a flavor of how that works, and then how we took those lessons learned from developing the chemistry for the electrochromic mirror to develop a organic battery. So the mirror, the element of the mirror, the glass and reflective part, is a sandwich. And the meat of the sandwich is the magic goo, which we call the EC medium or the electrolyte. The outer plates, the bun, are glass sheets that have a transparent conductive coating on the inside surface. And then there's a seal around the outside to keep everything from leaking. And what happens chemically, we start off with two compounds in there, A and C. And the white color is meant to represent the fact that they're colorless. And when we apply a voltage, we convert A to A plus at the anode, and that's green. A plus is green. And C converts to C minus at the cathode. One thing that's important to realize is that for every electron we take out at the anode, we have to add one at the cathode. So we can't just do half of this. We've got to do both sides of this reaction. And then for a mirror, it self erases, so it becomes colorless again, which is the 10-second shelf life, because A plus and C minus swim back together. The electron hops back from C minus to A plus, converts it to C and A, which are colorless. And this is a representative voltammogram showing both of those. On the right-hand side is the A to A plus duct. The left-hand side is the C to C minus duct. And so here, if we show this top curve on the right, that's where we're oxidizing A to A plus. As we switch the voltage back, we're now reducing A plus back to A. Similar thing to C on the other side, on the left side. So if you remember your freshman chemistry, which most of us don't, anytime that you make A plus, you also make a little bit of A2 plus. And it happens by this mechanism called disproportionation, where two A pluses combine and give you A and a molecule of A2 plus. Same thing happens for C. Two C minuses combine, give you back C and C2 minus. And you'll notice that in both of these reactions, I've drawn the arrows, bigger arrow to the left and a small arrow to the right. That is because it costs you energy to go to the right. But there's always enough energy there to generate a little bit of the A2 plus and a little bit of the C2 minus. And those, the problem there is that those undergo decomposition. And if we're constantly bleeding off those through decomposition products, we're constantly generating more, getting more decomposition. And until we can solve that problem, our electrochromic mirror is not going to last very long. Our organic battery is not going to last very long. So how do we solve this problem? Well, one way, let me back up for a second, is to try and make that equilibrium for both those reactions lie further to the left. And we know how to do that. And it works. I won't go into the details. It helps a lot. The other way is to try and make A2 plus and C2 minus as stable as possible. And for that, we need more ducts. So now we've got a system that shows 4 nice ducts. And the outermost pairs of ducts mean that A2 plus and C2 minus are relatively stable because they're nice looking ducts. Now they're not perfectly stable, but they're pretty close in this case. So our mirrors now last a long time, and it gives us hope that we can make batteries that will last a long time. So everything's great. It's going to work perfectly forever, right? Yeah. So not necessarily. one thing that we always have to account for is impurities. So things like if we have a slight air leak during manufacturing, the mirror will turn yellow or yellow-green. If we have a little bit of heat, heat helps an impurity react and will turn a mirror blue. And if you think about it, what I said before, whenever we generate A plus, the colored species, whenever we pull an electron out of A to generate A plus, we have to add one to B, to C, to generate the blue species. If you have any side reactions that chew up an electron, you're going to get out of whack, and you're going to have some residual color. So how do we take care of that? It's kind of like walking a tightrope. Unless you can account for every single electron and make sure that for every one that goes in, you get another one going out in the same where you want it, you're going to have a colored mirror. So it's like walking a tightrope. And we were wondering, is it possible to introduce additives that can soak up any excess electrons or impurities or any excess positive charges without a change in color? And obviously it's possible, otherwise I wouldn't have this slide here. And the requirements for what we're terming a redox buffer or a color buffer. In chemistry, a pH buffer is a system that resists changes in pH. This is a system that resists changes in color. And it has to be electrochemically active, not highly colored, it has to be compatible with other materials, it's got to be stable. And fortunately, we were able to find something that does that well. And now, you've seen this before, but now it looks something like, in the original self-erasing part, you get them swimming back together. But if you get out of whack, now we introduce a buffer in both forms, B and B plus. And if you get a little bit out of whack and you have some excess A plus, that second reaction underneath there, that A plus, the green A plus, will react with uncolored B to give you uncolored A and uncolored B plus. Same thing happens on the other side. If you have a little bit of extra C minus, it will react with uncolored B plus to give you uncolored B and C. And to show you how effective that is, well, first of all, you've seen this one before. This is what it looks like with the buffer. Almost the same, right? But if you look closely, there's a little bump here at about 0 volts and a little bump on the bottom side about 0 volts. That's the buffer. We only need a tiny bit of it to address the color change. And if we look at a test of how it performs, shows the red curves show, well, first of all, it's a plot of color change versus test hours. Color change sounds like a really nebulous quantity, but it's actually mathematically defined. And if you see a color change of more than 5, it is noticeable. Our first two generations, first generation there lasted about a week and then looks absolutely horrible. Second generation lasts a couple of weeks and looks horrible. The green line is for our buffered system. A year is a little over 8,000 hours. I actually threw a birthday party for these test samples because they were doing so well. And this is a brutal test. This is a test in a photo chamber that has a 5,000 watt xenon arc lamp that generates enough light to simulate noontime Miami sun 24 hours a day. So we beat the heck out of this system and it still survived. And that led us to the possibility of making electrochromic windows for Boeing. Boeing approached us and wanted to get away from their mechanical shades on their new 787. The mechanical shades are the #1 maintenance item for the airlines. They're also incredibly expensive, which I don't understand. But, well, I do because it's aerospace. And Boeing's tagline at the time was preserving the magic of flight. And they felt like with the shade all the way down, people were not getting the sense of flying like they did back in the old days with no shades. And this provides a way to get tunable light into the cabin. And so you can eliminate glare. And one of the most important features of this, I learned this, I had to present to about 200 maintenance people and stewards and stewardesses. And you want to know the thing that they were most excited about is that if they wanted to change the position of the shades, like on takeoff or landing, they could just go to the control panel and do it rather than reaching over a sleeping passenger with a rolled up newspaper. Now, and you think about it from their perspective, yes, I understand, but it was not a feature that we thought about until then. So the current ones go from, well, I brought one. I brought an early prototype, and this prototype goes from about 70% white light transmission to about 0.01% light transmission. And by the way, 70% is probably higher than these windows in this room. So it's not dim at all. It's very clear. And I will just show you this, and I would encourage you to come up here and play with it later if you would like. So I mentioned that this early prototype goes to about 0.01% light transmission. It takes about a minute, a little bit more than a minute. The new ones are faster, and they go to 0.001% light transmission. And the speed is actually, we could speed it up, but Boeing did not want an abrupt change in light because that tends to jar people. They wanted a gradual change in light transmission. And interestingly enough, you're even at 0.01 or 0.001%, if you're in a dark area looking to a light area, you can still see. Your eye has a dynamic range of about 1 million. So when your pupil opens, you're now 1 million times more sensitive than you are otherwise. Just 1 second. Actually, Gentex had some of these available for seeing the eclipse. And they're dark enough that you could look at the eclipse through these. So, sorry, you had a question.
Would this be feasible for home installation?
Yes. And I hesitate because the reason we chose aerospace is one, they're willing to pay for it. And early on in the manufacturing process, things are expensive. But secondly, it was a relatively small area. And that was a lot easier to deal with. As you get to larger areas, to get good uniformity, we have to slow things down. It's still doable, but it is not inexpensive. The other factor is that in the glass manufacturing process and the coating with the transparent coating, there's a certain number of defects. And let's say that you have 1 defect per square foot. Let's say per square meter. You can still make a lot of mirrors and just cut around that 1 defect. You can't make very many windows of decent size, you know, large 1 meter window. Pretty much everyone will have a defect. And these start off as point defects, but then become larger. And it's part of the glass coating process. Well, it's glass manufacturing first and then transferred into coating. So it's a lot trickier as you get bigger. Now, Gentex is addressing that with some new technology. So clear this up just for grins.
Just a comment. The first step forward will lead to more.
I'm sorry.
The first step forward will lead to more.
Yep, you're absolutely right. And that's what we're counting on. And it's often a step forward, 2 steps back. And then when we first started looking at electrochromic windows, if I had to predict a service lifetime in the field, 2 weeks. And then we gradually made improvements. And if at the end, when we started manufacturing for Boeing, I would say at least 30 years lifetime. And that's even at 40,000 feet altitude, where the UV radiation is 2x what it is at ground level. And usually, I will point out, most organic things, you think about if you take your shirt, a brightly colored shirt, and leave it out in the sun for a week, it's toast, right? Or a year. And these things have a lifetime of 30 years. Now, I won't do it now, but if we want to talk about some of the technology that went into this, I don't know how many patents are in this because we had to change everything. And one of the things you'll notice is Boeing is really concerned about weight. So this is a glass sandwich with very, very thin glass, low weight. And the new ones are actually thinner than this. And there's a host of other things that we had to do. But a very fun project. This is one of my favorite pictures found on the internet. There are a bunch of aerospace ophiles, I guess, who just monitor Boeing. They sit outside Seattle and monitor comings and goings. In the background, that aircraft called the Dreamlifter that looks like a beluga whale is for moving sections of the fuselage of the 787 so they can be put together. In the foreground is the Gentex jet. We're coming to talk to them about some factor in the production process. So I just find that really cool. Somebody probably ran our tail number, looked us up, bought some stock, and is rich now. I don't know. But one of the other cool things about working with Boeing is that they wouldn't tell us exactly what the production schedule was, which if you're manufacturing a component, that drives you nuts because you can't plan, you can't train people, you can't staff people. So we monitored their production schedule by Google Earth. You can't hide a 787. So they were parked out on the tarmac and we knew which one was which and how fast they were going to go in for interior fitting. And because I was getting yelled at a lot for not knowing the production schedule. And then we figured out the Google Earth angle. And when that plane took off for its maiden flight, that was a really fun day in Seattle as well as in Zealand. And you may recognize that guy in the bottom right picture. He operated our windows and proclaimed our technology as nifty. And when the president of the United States calls your technology nifty, you know you got it made, right? So I've got another picture of him after it changes colors and he's just gone. It's really cool. So, hopefully we have time to talk about batteries. Sorry about that. What if we design our device instead of being an optical device like a mirror, that we use it to store energy? So what changes do we need to make? Well, first of all, things that are less critical are color changes, either design color changes or changes due to decomposition color changes. We don't care. We're not going to look at the stuff. Well, we are, but it's not a huge issue. We don't have to do ultra long-term cycling. I mentioned the windows or mirrors can do 100,000 cycles. That's overkill for an energy storage device. If we could do 10,000 cycles, that's switching one time a day, that's 30 years, almost. And we don't really care about UV degradation because they're not going to be exposed to UV. So that's great news. On the other side, the improvements we need to do, we need to make a higher oxidation potential, because the harder we make it to take an electron out, the higher the voltage of battery. Also, we need a lower reduction potential. Again, the harder it is to add an electron, the higher the voltage in the battery, which means the higher energy density. We also need increased solubility. So we need to cram as much of this material into our fuel or electrolyte as possible. We can get a color change at relatively low concentrations. We probably need 30 times, maybe a little more than 30 times the concentration that we have in here to really make an effective battery. We're going to be pumping this stuff, so we need lower viscosity. And for solubility, we need about 1 molar, for those of you familiar with that technology. We also need lower viscosity, and that's really hard because usually if you put anything at 1 molar in solution, it looks like honey if you're lucky, molasses if you're not lucky, Vaseline if you're really unlucky. And it's got to be cheap, very cheap. So the first thing we did was to look at how to increase oxidation potential. So we tried something that most people thought wouldn't work, which is cool. I love those things. And if you take that picture on the lower left, you know, we draw these things in 2 dimensions when we draw the structures on paper, but they're really 3-dimensional. And this thing looks like a butterfly or, you know, basically a butterfly. And when you pull out an electron, it flattens out. So we said, what if we put some shrubbery around there, which makes it harder for it to flatten out? And that's shown in the upper right-hand corner. We put these big groups on here. Now, interestingly, most people predicted that that would decrease the oxidation potential because of chemical characteristics. We said, no, we think it'll increase it. And it does. And if it didn't, I wouldn't tell you about it. But so this is the motion that it undergoes when it oxidizes. So this is just going from the normal form to the oxidized form. And unfortunately, I couldn't animate the other one, but you can see how with that extra bulk, it's interferes with the flattening. And turns out it works. So that's cool. We solved that problem. The next problem is to try and get a lower reduction potential. And I'll go through this pretty quick. If you look at that compound after the first arrow up top, this compound right there, if you put that on an organic chemistry exam, your professor would probably say that's nuts, that can't happen, that won't work. But in fact, they're stable compounds. We found some old Romanian literature that showed us the root here. We can make these things, we can put those in a bottle, but more importantly, we can take those on and make new compounds that are on the right side of the equation there. So we start off and make a bunch of different derivatives, both the upper and lower rings that we've changed. We've now made quite a few of them. And we show good ducts. This is actually the same compound run at different potential sweep rates. And so it's sort of a duct growth chart. But that's exactly what you expect for a well-behaved system. And it says we've made over 40 derivatives. This is an old slide. We've probably made 100 now. And they have very low reduction potentials. Remember I said we needed that? This triangle, well, first of all, this one marked FC is sort of just a reference here at 0 volts. Everyone used this one marked MV2 plus at about minus 850 or so, 850 millivolts. There was a report or two of this one at about minus 1 volt, the ACPY. The rest of these are all us. We sort of did this march down to more negative potentials, which we want. And the ones that I'm talking about today are these last two, well, in that range, 100 compounds in that range. Now, interestingly, we did some machine learning to try and improve the solubility and understand the solubility. And we found this really interesting correlation between structure and solubility. And I can tell you about it later. It's kind of complicated. But again, when we first noticed this correlation through machine learning, everybody thought we were nuts. So you might notice a common theme in stuff we do. But it was interesting. These are the compound structures. And if you compare the one on the lower left has very low solubility, and the one on the upper right, very similar structure, differing only by the top group, the OME group, very small perturbation. We get, what is that, a factor of 5, 6 increase in solubility. And we're now over 2 molar in solubility. Remember, our target was 1. So that's really good. But when we put 2 molar in, how viscous is it? Because we got to pump this stuff. Well, in this very scientific experiment here, we're comparing water on the right-hand side tube, the vacuum pump oil, which is not a very viscous oil, but it is significantly more viscous than water, on the left-hand side. And then in the middle is our compound at 2 molar. And again, very scientific. But you can see that it has quite low viscosity. In fact, at about 2 molar viscosity in our chosen solvent, the viscosity is about the same as water, pure water. So that's cool.
Any estimates about the impact of machine learning in this case? How much time did it save? How much did it increase the potential for finding a solution? I mean, because that's pretty dramatic to me anyway.
So the question was, how big a help was machine learning? And it was extremely significant, because the reason for the correlation between structure and solubility was counterintuitive. We never would have guessed. Basically, it's an attractive interaction in the crystal, which normally means you have lower solubility. It turns out that this particular attractive interaction gives you higher solubility. So would we have ever found it without machine learning? I doubt it. And so now we're applying machine learning to things like stability. And we haven't been doing that very long. We're already seeing, in fact, just this morning, we're predicting a structure to have 1,000 times higher stability than the ones we've made just through machine learning. So it's made me a believer. So these are some compounds that we made. Now we're introducing a new twist here. And the twist is that we now link together our positive fuel and our negative fuel, our stuff that can be oxidized and our stuff that can be reduced. And the reason that we do that is because in a normal flow battery, you have a separator, an ion exchange membrane between your positive fuel and your negative fuel so that they never mix. Because if they mix, first of all, you lose energy capacity, lose battery capacity, and now you have to purify this stuff and it's a mess. We've tied them together. So now we make the neutral form, and then on one side we put the positive form and the other side the negative form. And during discharge of the battery, the positive form goes neutral, the negative form goes neutral. They're the same thing. We don't care if they mix. So we can take that $800 per square meter ion exchange membrane that doesn't even work very well and requires frequent replacement, and we can replace it with porous polyethylene at about $2 a square meter. So we're starting to address the cheap part of this. So we've eliminated the vanadium, which, as I mentioned before, was expensive. We've gone from the expensive ion selective membrane that doesn't work to a simple porous separator. Because we have a non-aqueous solvent, in aqueous media, you're limited to, thermodynamically at least, you're limited to about 1.2 volts, maybe a little higher if you get lucky. By going to a non-aqueous medium, we go much higher voltage. In this case, we're targeting 2x voltage, which we're not there yet at a durable system. We can also do multi-electrons at once. So instead of going to A+, we go all the way to A2+. And if we're sure that's stable, works like a champ. So we double our energy and power by going to higher voltage. We double it again by going to 2-electron system. So here's where we're at now at increasing the voltage. We have systems that go as high as 2.73 volts, which is pretty good. It's not as high as lithium, but it's pretty good. We have systems that are 2 electrons. This is about 2.4 volts, but 2 electrons. Again, I'm not sure it's durable enough for real world, but we're tweaking structures. And then just for fun, we made this enormous molecule. It has 4 ducts, but every duct is 2 electrons. So we have 4 electrons on the right-hand side total, 4 electrons on the left-hand side, which is the first 4-electron system for a battery that I'm aware of. Now, you'll notice, though, we do have a deformed duct on the far left. I think we know why, but it probably means that this is not going to work very long. It's also a gigantic molecule. So, in terms of solubility of the link systems, before I get to these test results, I'll explain those later. It's too distracting now. We've reached 1 molar of our link system in the electrolyte. And to me, this is astounding because our electrolyte weighs about 1,200 grams per liter. 800 grams is our compound. And then we add an electrolyte to help us, to help facilitate electrical current flow. That's another 300 grams. And if you're doing the math, that gives us 100 grams left for the solvent. So we dissolved 800 grams of a solute in 100 grams of solvent. And it's still not very viscous. I don't know how that happens, but anyway, this thing is not going to go in that high. I guarantee it. So here's some early results that we had. And this is complicated. Don't worry about the details. The bottom graph shows charging and discharging. So what we do is we apply a constant current and we watch the potential. And you can see initially it rises very quickly and then it sort of plateaus. And then when it starts to turn up here at the end, that means that we're done charging, basically. And the other curve is the discharge, the one that's downward going. And again, we go through a plateau and then a rapid drop off, and that means we're done discharging. What we're looking for is no change over time. And we clearly fail here in that. And the reason we fail is because of the way that we had to run this experiment, we're very sensitive to contaminants, and we know there are contaminants there. So the curve on the right is first charge cycle, second, third, fourth, fifth, sixth, seventh, eighth. Shows the first 10 charge cycles in red and first 10 discharge cycles in red. And you can see that we're losing, I don't know, 25, 30% of our battery capacity. The black curve is cycles 90 through 100, which really lie on top of each other. And that tells us when we use up all the impurities, we have a very stable system. So this was extremely exciting for us. And in fact, we've gone on, we've now shown, and I don't have the same graph, but here is we're plotting on the left-hand plot in blue is the charge, sorry. Come on. Yep. Why won't it stay? There we go. The blue line is the charge capacity over cycle time. The sort of brownish gold line is discharge capacity. So first of all, you see that we're pretty close in charge and discharge, which is very good. So we get, in this case, about, let's just say 80%. I think it's actually higher than that. 80%. It's probably closer to 90% of the energy we put in the battery we get back out, which is very good for these types of systems. And then you also see that we don't have very much decay. We see a 12% capacity loss after 1,000 cycles. And even better news than that is that we only see a 2% decomposition after 6,000 cycles. And you might ask, why the difference there? We think we understand that now. But the fact that we don't see the chemical loss means that we can do better than this 12% capacity loss after 1,000 cycles. So that's pretty, sorry. So that's pretty good. And we're pretty excited about that. So just to summarize, one of the take-home messages I want to pass along is that organic compounds can be pretty durable, even in very demanding real-world applications. We can achieve high voltage, high energy. I didn't talk much about high power, but we think we can get probably 4 times the power of vanadium flow batteries, power density. And we're already slightly ahead of them on energy density. I think we can probably get maybe as high as twice as energy dense as vanadium. And we can do it all but at much lower costs. No vanadium, no ion exchange membrane, And importantly, we have a very non-toxic, safe electrolyte instead of sulfuric acid. So all the precautions that you have to take, stainless steel plumbing, special pumps, secondary confinement for the electrolyte in vanadium, we can use polypropylene jugs, polypropylene tanks and plumbing. And again, we think we have an answer. Now, there is no one single answer to all our energy storage needs, but we think we have part of the answer. We have very good collaboration with two groups at MSU, actually. The first picture here shows the David Hickey group. That looks like they're having fun. This is Sharmila Samaru, who will be joining us in a few weeks at Jolt. So we're excited about that. But we have had great support from Michigan State, for one, from Hope College. We've also gotten funding from the DOE and the NSF. Community Foundation and Holland Zealand contributed to my MSU work, my MSU lab work. So most of these inventions were made in my MSU lab and then owned by MSU now. Jolt has licensed the IP back. We have, a couple of years ago, I spent 2 years at Argonne National Lab in what they call a lab embedded entrepreneurship program, which was cool, except for COVID. We also have gotten support from Shell Oil. They sponsor work at National Renewable Energy Lab. There was a competition for startup companies, 40 finalists, and we were one of the 3 chosen for support, which was cool. And this is my summer group where I run the summer internship program at MSU Bioeconomy Institute. This is from a couple years ago on one of our Hawaiian Shirt Fridays. Brett apparently didn't get the memo. I don't know. But we have a lot of fun. We typically have 5 to 10 interns during the summer, and then a number of them continue on during the year. And we've had every one of them go on to grad school or industry. 2 of them have started their own company. They're all very successful, which is pretty cool. And several of them are on patents for that Jolt is now licensed. So
We have one question from Russ. He says, how soon will this be available for the public?
I don't know, Russ, how much money do you have? No, seriously, it's scientists, and it's a very valid question. And scientists hate those questions because it's so hard to predict. We are targeting pilot installation late 2025. We have received some investment. Right now, we are in the middle of a Series A round. So we're trying to raise $5.6 million, which will help facilitate us getting there. This is not like software development that can be done with relatively small amount of money. This is hard tech, and I mean hard in every sense of that word. Just making the initial batch of compounds at large scale will probably cost 6 figures. So let's just say $100,000, and at some point we'll reduce it to $1,000. But the first one is tough.
Allow me to piggyback on that question. Once the pilot testing is done and it's successful, the prototype is stable, what does the team envision the first wave of clients would be? What industry, what sector might it be?
So that's a very good question. The question is, what is the first sector, the beachhead market, so to speak? And unfortunately, I think it's set up that we have a very tough initial market, and that's utilities for grid backup. I think eventually we'll get down to low costs for individual homes. But we're not going to be able to do that initially until we get the economy of scale. So we have that. We're also looking at some niche applications that I'm not sure I can talk about just yet. So
Worldwide, what is the impact of this? Other countries trying to sneak in? I mean, things don't
absolutely.
stay silent forever.
No, there's a number of academic groups as well as industrial groups that are working on flow batteries in every kind of flavor you can imagine. Aqueous batteries, what they call hybrid flow batteries, semi-flow batteries. There's an international flow battery forum. There's a DOE workshop next week that I'm supposed to go to in Seattle. So there's a lot of competition and some tough competition too. You know, non-aqueous has the advantage of higher voltage. Aqueous has the advantage of their solvent is free, basically. So they're every variation you can think of. There are a lot of smart people out there, and you know, fortunately, we have several of them that we employ. But there are a lot. There's a lot of competition. Yeah.
You said, I think, 2025 for a pilot installation. What kind of megawatt or kilowatt capacity per hour are you planning for?
So the question was, in our prototype installation scheduled for 2025, how big is the system? So we'll probably have an intermediate step first, just at let's say 2 or 3 kilowatts and maybe 10 or 12 kilowatt hours, which is not a lot. The later one will probably be the pilot will probably be around 25 kilowatt. So and I did bring a demo for just to show you what the flow battery, this is what the electrochemical cell looks like for the flow battery. Now this is lab scale and it's not efficiently designed for size or weight. This is just one cell. We will probably have stacks, first of all, that are probably about 1 meter by 1 meter, and then 40 of these stacked up, not with an end plate all the time. So it'll look like, actually it'll look like this, sort of the size of a dorm size refrigerator. And then you'll have warehouses full of these refrigerators. So that's what we envision. But we won't get there overnight.
Gloria, you have a question from cyberspace.
What is the end life? What is the life of the battery, and what are the products that need to be disposed of at the end of life?
So the question about lifetime of the battery and disposal of the electrolyte when it's done. So we are shooting for at least a 20-year life. Utilities are not known for their risk taking, let's say. So they want guaranteed life. And if Jolt puts a 20-year lifetime on it, that won't be acceptable enough, because Jolt could go out of business in less than that if we don't have a good system. So we need a partner that has is able to guarantee the life. And to do that, obviously, we have to show some really good test results. And just like we did for the windows, beat the heck out of our system. As far as disposal goes, and we just had a discussion on this morning, we think we can regenerate them quite easily, regenerate the active materials from the known decomposition products. So that, and that's, so you don't need to replace the fluid, you just treat the fluid and then reintroduce it, which would be really nice. If you do have to dispose of it, it's pretty benign stuff. Our major component, the electrolyte solvent, is very benign substances. The EPA classifies it in the same category as things like corn husks. So.
A couple of years ago, someone from the MSU Bio Lab here in town gave a talk about kind of like organic batteries. And at that time, they were anticipating doing a joint test with Holland BPW. Is that in any way connected with your work? And are you thinking of maybe trying anything with our local Holland BPW?
We've had discussions with BPW and they've offered us a site. So we want to make sure it works first.
Yeah, similar discussion. I was thinking about a JV between you and Gentex. Is that, or have those discussions been underway?
So Gentex is an investor in the last round as well as this. Well, it's not finalized, let's say, but they are a current investor, so I can say that. And we see lots of synergy there. They have a lot of expertise in areas that we need. Yeah, I can't say that. So we see that as a very fruitful discussion.
Not sure how to ask this. At the point where this becomes commercially viable, what kind of watt hour density are you expecting compared to lithium ions that are current lithium ion batteries?
Okay, so the question was about energy density, lithium ion versus our technology. So lithium ion is really good. They're comfortably probably about 300 watt hours per kilogram for the best cells out there commercially available now, and it's continuing to go up. We're not going to reach that. We're not going to come close to that. So for your Tesla, you still want your lithium ion battery. But if you're just going to buy a battery, park it on a concrete slab, that's where we think we can have impact, because we'll be a lot less expensive. We'll have a longer life. In energy density, if you're not moving around all the time, is just less important. We'll be safer as well. The other advantage of flow batteries is that they're scalable. So early on, if you decide that you need a 2 megawatt engine and you want to store 4 megawatt hours, you can do that. But if later you need to store 12 megawatt hours, you just add more tanks. Very simple. You don't have, with lithium, you buy the engine and the tank, engine and the tank, engine and the tank, engine and the tank every time. It's like if you have to move 50 people from point A to point B, you could give them 50 cars and it'll work, right? Or you could get one bus. And we can do it with a bus.
Any other questions? I'd like to make a couple of points before we end. First of all, you're welcome to go look at the electrochromic window when we're done here in a moment. Secondly, your point about the amount of work being done in this area around the world. I've been astounded by how many times I've been invited by the Royal Society of Chemistry to attend a webinar on how to improve my batteries, how to test my batteries. A lot of work is going on around the world in this area. And if nothing else, we learned a lot today. The take-home message is that electrochemists and ornithologists have something in common. They both say we need more ducks. Thank you very much, Dr. Guarr, for the presentation. We've learned a lot, and hopefully you'll come back and join us again in the future.
Thank you. Thank you.